All right. What I like about this problem is that it is very real life because most of our satellites that we do have are geosynchronous satellites, meaning that almost all of them are up at a particular height above the surface of the Earth, so that they're synchronized with the Earth's rotation. And the advantage of that is they move with the Earth's rotation. So whatever satellite we might have that's directly over our head right now is going to always be directly over our head. Actually, these satellites are pretty much in the equatorial plane. So what I mean by that is if we have the equator, then what that means is that all of these satellites are in the equator's plane, meaning that they're going around the Earth, but they're going around within in the plane of the equator. And so as the Earth rotates, the satellite will be moving with it. So we know how fast the Earth rotates. So that's not something, even though it's not given in the problem, since we know the rotation rate of the Earth, we should be able to figure out how high these satellites need to be above the surface of the Earth. So I'm just going to put the satellite somewhere over here for now. So there's my satellite. And the only thing that's causing that satellite to change direction is the gravitational force of attraction between the satellite and the Earth. So we're going to have a force in that direction. So that's the gravitational force of attraction. So that's my picture. From my picture, I can write my descriptive equation. So I'm going to sum up my centripetal forces, which are the forces that cause the change in direction. And in this problem, it's going to be the gravitational force. Now it's going to either equal mv squared over r or mr omega squared. They're the same thing. They're ma. So whenever you're writing your descriptive equation, it's always F equals ma. So there's the F, and I want to write ma over here. Well, I want to write it in the form that's going to be useful to the solution of this problem. And in the problem, we're actually looking for the height above the Earth's surface that these satellites revolve. So we're looking from the distance from here to there. Well, in order to get the distance from here to here, I'm going to get the distance from here to the center of the Earth, because that would be the orbital radius of the satellite, the radius of the satellite's moving through. So because r is the unknown, you don't have a choice. You cannot use mv squared over r here, because if you do, your r will be hidden in the variable v, and I need all my r's exposed. So you have to use mr omega squared to solve this problem. Once you have that, now I'm just going to replace my Fg with the formula for Fg, where it's written in terms of the universal gravitation constant, the mass, and the r. So the left side is going to become G. Now it's M1, M2. I'm going to actually not use a subscript for the M of the satellite, and I'll use E for the subscript for the mass of the Earth. So I'm going to write this as Gm me instead of M1, M2 over r squared, and that's going to equal mr omega squared. Now, this m is the same as that m, because these are the two masses that have an attraction to each other, the mass of the Earth and the mass of the satellite. The mass of the satellite is the one that's moving through a circle, so that's why these two are the same. So since they're on both sides of the equation, I can cancel them out. Now, my unknown is r. So to solve for r, well, actually, if we just follow our algebra steps, the first thing would be, if the equation contains fractions, multiply by the least common denominator. So the least common denominator here is r squared. So when I multiply the left side by r squared, the r squareds cancel out, and I'm left with G me. When I multiply the right side by r squared, I'm going to get r squared. Nothing's going to cancel here. I'm going to get r squared times r. So I'm going to get r cubed omega squared. Now to solve for r, all I need to do is divide both sides by omega squared. That'll get the omega squared down here. And then take the cube root. So we're taking the cube root of r. And if you actually look at your units, we should get the answer in meters. We could check that at the end. So when everything's rearranged, I'm going to get r is going to equal the cube root of g me over omega squared. Now, I know what g is. It's a constant. It's on your formula fact sheet. I know what the mass of the Earth is. It's on your formula fact sheet. We need to get the omega in radians per second in order for this formula to work. So I know how fast it takes for the Earth to rotate once. How long does it take for the Earth to rotate once? 24 hours. So that means that the satellite has to revolve around the Earth once every 24 hours. So we're going to, I'll solve it over here. So omega is 1 rev every 24 hours. And I'm going to convert that into radians per second. So I'm going to have to do that in 2 steps because I need to get rid of revs and I need to get rid of hours. So I'm going to have rev to radian, and I'm going to have hours to seconds. In 1 hour, there are 3,600 seconds. And in 1 rev, that's equal to 2 pi radians. So I'm not using the radius of the Earth here, or the radius of this. I'm using 2 pi radians equals 1 rev. And if you solve that, what do you get for the omega? Somebody should have this answer if you actually did this as homework like you were supposed to. Yes. Okay, in scientific notation, then that would be 7.2. Is there a number after the 2? I thought it was 7.27. Rounded off. What's after the 6? Do you know? So it would be 7.27 times 10 to the, what's that? Negative 5. Negative 5. All right, so now that we have that, we have all the numbers to plug in. Do you know how to put the cube root in your calculator? There's a couple ways you can do it. If you have trouble doing it, let me know. I'll show you. But we're going to put in, for G, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. We're going to put the mass of the Earth, 5.98 times 10 to the 24th kilograms. And we're going to put the angular velocity as 7.27 times 10 to the negative 5 radians per second. And that's going to get you your answer for that. Well, actually, what that's going to get us is the orbital radius. Remember, the question said, what's the height of the satellite above the Earth? So I actually need to subtract away the radius of the Earth to get the height above the surface. So I think if you solve this, don't you get like 4.22 times 10 to the 7th, this number? If you have trouble getting it, I'll explain in a second, but 4.22 times 10 to the 7th meters, I believe that's the answer that you get for the R. And since the question specifically asked for the height, I'll do it over here. The height is going to equal that number, 4.22 times 10 to the 7th meters, and I'm going to subtract the radius of the Earth, which is 6.38, or actually, because of the numbers that I have here, I know how many digits I'm going, so I'm going to just write this as 6.4 times 10 to the 6th meters. Because what that is, if I write this times 10 to the 7th, that would be 0.64 times 10 to the 7th. So if that's 10 to the 7th and that's 10 to the 7th, then I'm basically just subtracting 0.64 from 4.22. And that'll get me the height. So that's going to be 3 point something. What number did I give you for that? 3.59 times 10 to the 7th meters. So there is your answer. Now let's look and see what that actually means on the picture in terms of how far away that is. If I actually go, so from here to here is 1 radius. The number that I just gave is about 6 radii above the surface of the Earth. So if I take that amount, so whatever that is, so I'm going to go 1, 2, 3, 4, 5, 6. So that's where these satellites actually are above the Earth. If the Earth was that big, then these satellites are way out there. They're pretty far away, which is actually pretty good because being that far away, we don't really have to curve the signal to the satellite from the Earth. Because if I just look at, like from here, it would be hard to actually get a signal from here because of the Earth if it was here. But when it's way out there, then I can send a signal out in this direction, bounce it off the satellite, and get it to a different location on the Earth. That's the thing is when these satellites, before these satellites, we couldn't communicate with the other side of the Earth. Now we have these satellites, we can send the signal off of them and bounce the signal off the satellite so we can communicate with the other side of the Earth. Like when Nixon went to China, I remember the big thing was that was the first time we had like a live televised communication from China. With China being on the other side of the Earth, we couldn't do it. But using the satellite, we were able to bounce the signal. I remember when they showed it, and it was a little bit grainy, like it wasn't like perfectly clear, but we could still see what was going on.